Okay, so this is the exam feedback for the Evolution of the Living Earth course, part D, so the global biogeochemical cycles questions, the last part of the exam. So if you've not already watched the feedback for part B, so the climate questions and the kind of general advice, that is something that you should do if you're interested in answers in life in general. And some generic exam question advice, answering advice, in fact, also question advice. Yeah, so that's linked somewhere down below. Hopefully, if I can figure out how to do that. But anyway, so we're going to crack on with the rest of the questions now. So the two questions for the biogeochemical cycles. One was about the pH of the ocean and how that is related to CO2 in the atmosphere. So lots of lovely stuff to write about there. And then the last question, not answered by a huge number of people, which was a shame because so much fun to write, was about dimethylsulphide and how that affects climate through a feedback mechanism. So we'll come on to those in turn, one by one. Here we go. Yeah, so just to have a quick look at the overall mark distribution, a little bit lower than for the other parts of the exam. This is probably due to it being the end of the exam, so maybe you didn't finish, didn't spend so much time on this section. But anyway, so lots of room for improvement here in exam technique, perhaps, but also in some of your question answering skills. Right, so question 7, so the first one of the last part, is a question about how CO2 is linked to pH in the ocean and acidity, okay, and what really controls that. So again, split up into 3 parts, 2 short kind of parts which require shorter answers, and then a more substantial large part. And I think one of the reasons why people did a little bit more poorly on this question than some of the other questions was because they gave good answers to the first parts of the question, but really didn't grasp the last part where a large proportion of the marks were available. So when you're picking which questions to do make sure that you look through and identify where your kind of knowledge base is, and whether if that coincides with the kind of the big bucks when it comes to points for questions. Okay, so the first part, again, instructing you use relevant chemical equations, equilibria, to show something. Okay, so your answer really must have chemical equations in there. So the really question is asking how CO2 affects the pH of the ocean. Okay, and some start off with is really how does CO2 get into the ocean? What is pH? So these are things which you really should have in your answer. So importantly, a definition of pH would be nice. Okay, and this is important because it shows that pH is really a measurement of the concentration or how much hydrogen ions are dissolved in the water. So we're really looking for changes in hydrogen ion concentration and how CO2 can change those. And the other thing that's important is that CO2 can get into the ocean in the first place, and it does that because it's a gas and it can dissolve into the ocean by Henry's law, which is dependent on temperature. That temperature dependence not so important for this part of the question, but it is important that gas can dissolve into the ocean. So the next thing really is to have these chemical equilibria that really show that when CO2 dissolves into the ocean into aqueous CO2, it reacts with water and forms these kind of other carbon-bearing species, carbonic acid, bicarbonate and carbonate ion, and those release these hydrogen ions. So with just these equations and the pH definition, we can show that if we add CO2 to the atmosphere, okay, so if the concentration in the atmosphere goes up, that will go into the ocean. That will cause there to be more hydrogen ions, okay? And that means that because the pH is the negative log of the hydrogen ion concentration, it will make the pH go down. Okay, so that's really the crux of the first part of the question, and then the second part is really asking that question in reverse: is if we can change pH of the ocean some other way, how will that impact CO2 in the atmosphere? So again, we can refer back to some of the equations that we wrote for the first part of the question, and show that if we are changing the pH, we are changing the hydrogen ion concentration. Okay, and that will force these equilibria over to the left-hand side. Okay, so the important thing here is that changing the hydrogen ion concentration changes the proportion of these different carbon-bearing species, and that's what's shown in this kind of like diagram at the bottom. You don't need to have this diagram to answer the question. It would be nice, but it's, you know, it would be a bonus. But what it's really showing is that at different pHs, the proportions of the different carbon species that are dissolved in the ocean are different. So at low pH, we have higher concentrations of aqueous CO2 for any total dissolved CO2, or total dissolved carbon, sorry. The next bit, which quite a lot of people missed out on, is the really important kind of point that only the CO2, only this CO2, only the CO2 species of all of the dissolved carbon species can interact with the atmosphere. It's the only one that has a gaseous phase, so only this one can interact with the atmosphere. And this is really important because this means for any given amount of carbon in the atmosphere-ocean system, if you just think of the atmosphere and ocean as kind of a closed system, you're not taking carbon in and out of that, but you can take carbon from the atmosphere, put it in the ocean, or the other way around. If you have a very small proportion of the dissolved inorganic carbon as CO2, you can store loads and loads and loads of carbon in these other species over here, which these other species, sorry, I'm using the wrong point, these other species, bicarbonate and carbon dioxide, that cannot interact with the atmosphere. So if the pH goes down, we have more CO2 aqueous compared to the other dissolved carbon species, which means more will go up into the atmosphere. Because Henry's law really states that it's the ratio of this box to this little box here, that ratio will stay constant at a different temperature, at a constant temperature. But if we can therefore take or carbon out of these two boxes and put them into this box, then if the ratio of these two stays the same, then the concentration in the atmosphere will go up, and that's kind of explained in this diagram here, which we could recall from the lectures. Another way of looking at it is how much carbon can be put in the ocean, and at higher pH, we can store more carbon in the ocean, therefore less in the atmosphere. Any given amount of carbon in the Earth, in the atmosphere-ocean system. Okay, so that's really what we were kind of looking for in that question, referring back to the equations that you would have written down for the first part, and critically explaining that only the CO2 can exchange with the atmosphere. So by changing the proportions of the dissolved species, okay, and keeping this ratio between the atmosphere and the ocean CO2, okay, as opposed to the ocean total dissolved carbon, by keeping that ratio constant, you will therefore must be increasing the atmospheric concentration. Okay, just point out there that only CO2 can dissolve with the thing there. I should have moved that animation to somewhere else. Anyway, too late now. Right, so the last part of this this question was really where I guess most of the marks were, and I guess also where most of the marks were lost, sadly. So we're really asking for more of a full description here of processes and conditions. Okay, so that should be a little bit of a clue that you're looking for a condition, so that's kind of like a state of the environment, so the temperature or the salinity or the amount of precipitation, something like that's a kind of a condition. And then also processes, okay, so things that happen within the ocean or things that happen in the atmosphere that can control the. Now this is another part of the question which kind of many of you didn't seem to grasp, the relative proportions of inorganic carbon stored in the ocean versus the atmosphere. So what this question is not asking, it's not saying what will cause the atmospheric CO2 to go up or down. or what will cause the total carbon in the ocean to go up or down. What we're really looking for is how can you change the ratio of carbon in the atmosphere to the carbon in the ocean. Okay, so it's not just looking at adding more carbon to the atmosphere or taking it away. It's really changing the proportion between the two. Okay, so that's where I think quite a lot of you got a little bit led astray by this question and didn't provide the answer to the question that was being asked. Okay, so some things that you might also want to think about in terms of this answer. I mean, what is inorganic carbon stored in the ocean? If you want to define what that is, and then thinking about what are these processes or conditions. So first of all, the dissolved inorganic carbon in the ocean are the sum of those dissolved carbon species. So the CO2 aqueous that's dissolved from the atmosphere, and then the carbonate ion and the bicarbonate ion. You could also add the carbonic acid species as well, but that is in such low quantities that it is insignificant. Okay, you would have got some bonuses if you said that, but nobody did. So this is I guess a picture of the carbon cycle stolen from the IPCC, which I've put into the lectures. So what this question is really asking is not so much how much carbon can get up into the atmosphere or how much carbon can get into the ocean. It's really looking at these boxes here, so the inorganic carbon box in the ocean and the atmospheric carbon reservoir, and how can we basically look at the exchange of carbon between these two boxes. Okay, so what changes the size of this box relative to this box? Okay, so if you were to, for instance, burn lots of fossil fuels, cut down lots of trees, burn them, or maybe change weathering, that will change the amount of carbon in the atmosphere, but a proportion of that carbon will go into the ocean, and ultimately the ratio between the two will not change. Okay, so that's not what we were asking. Okay, now what I've just said there is not strictly true for all cases. So if you, for instance, change the CO2 in the atmosphere through weathering, that will also have an effect on ocean chemistry, which will change the proportioning of carbon between the atmosphere and the ocean. Now, if you'd have gone through that whole argument about saying how weathering changes the proportions between the two, but it also changes the total amount, that would be okay. But if you just went in with your answer and said atmospheric CO2 concentration goes up or down because of these processes of weathering or fossil fuel burning, that is not answering the question. Okay, so again, I guess the marks available here to a certain extent for repeating earlier parts of the question in terms of how can we change the proportion between the atmosphere and the ocean. Just changing the temperature, because that affects the solubility, would be a good part of an answer that you could start thinking about. Similarly, pH. The pH, if you can somehow change the pH of the ocean, either through adding CO2 or some other process, maybe adding alkalinity through weathering, the change of the pH of the ocean will change the proportion of carbon that is in CO2 versus these carbonate and bicarbonate forms, and therefore will change the balance between the atmosphere and the ocean. Okay, so those are things that you could put into your answer. But what quite a lot of people really missed was this processes part of the question, in terms of saying what are the processes which would be changing pH, what are the processes which would be changing temperature. And one of the things that was really kind of missed out on by many people was that the ocean is not a single kind of body of water. It has a surface kind of ocean and a kind of a deep ocean. And really importantly, only the surface ocean kind of really interacts with the atmosphere, okay? Because gas can't get from down here to up here without going through the surface ocean. Which means that if you can take carbon out of the surface ocean and put it into the deep ocean, okay, then you can change the ratio of carbon in the atmosphere to the whole ocean. Okay. So one thing that was really missing from many of your answers was some mention and then description of how we can take carbon from the surface ocean to the deep ocean, and also importantly how we can get it out of the deep ocean into the surface ocean. So these are I guess one of the ways that we can do that is with changing the pH of the surface ocean and changing the pH of the deep ocean, and some people kind of went into that a little bit. But what was really missing from many things was the carbon pumps. So the organic carbon pump. There's also an inorganic carbon pump, which if you'd have done a little bit more reading, then you'd have known about that as well. But really importantly, that in the surface ocean, all kinds of life happens. That life makes kind of organic carbon, also makes inorganic carbon, which does a different thing. And that takes CO2 out of the surface ocean and puts it down into the deep ocean, okay, where it is respired or remineralized. So if you look at concentration profiles of total inorganic carbon, we can see that the ocean has a lower concentration in the surface than in the deep ocean. Okay, so this process is adding carbon to the ocean, effectively taking it out of the surface ocean, which means that it's ultimately taking it out of the atmosphere. So if this process is more vigorous, then we will change the proportion of carbon in the atmosphere versus the ocean. Okay, we'll put less in the atmosphere, more in the ocean. Similarly, if we make this process less effective, or we make the return flux, so which is by mixing or upwelling, if we make that flux more strong, then that will have the opposite effect. Okay, that will make the ratio between the atmosphere and the ocean lower. Okay, yeah, higher. Sorry, there'll be more CO2 in the atmosphere, less CO2 in the ocean. Okay, so it was that aspect that was missing from quite a lot of your answers. The concept that you had to look at different processes, different conditions, and describe them. And what was really missing from many of your answers was this idea that the deep ocean is separate from the surface ocean. So if you can change the fluxes between them, then you get good times for changing the proportions of carbon in the atmosphere and the ocean. Okay, so on to the last question now. Two parts, equally weighted here. So we're really asking for some explanation of how dimethyl sulfide, how it gets from the ocean, and how those emissions affect climate, and then really looking for how these might change in the future. Excuse the noise, somebody is smashing up a car outside of campus. Anyway, so the first part of the question, how do natural emissions of dimethyl sulfide arise? Okay, where do they come from? And how do they affect global climate? Okay, so I guess, so if we split this up, again, rewriting the question in our own words to try to identify the different parts, make sure we're answering everything. So first of all, they're very noisily smashing up my car. How is dimethyl sulfide produced in the ocean? That should be your answer. And then this was a bit that was missed quite a lot. It's produced in the ocean, but how does it get out of the ocean into the atmosphere? So if it wants to affect the climate, it has to be in the atmosphere, and it's produced in the ocean, so go figure. And then how does it affect the climate? And a little bit of kind of maybe extra detail you could put in here is not just how it affects the climate, warmer, colder, what mechanism does it use to do that, but maybe add some detail about the kind of timescales over which this process can be effective. Okay. So I guess first of all, dimethyl sulfide is produced by the decay of organic matter. In the ocean, that's largely the decay of phytoplankton. So these, when you have these big blooms of organisms, then you have growth and then death. Everything dies. Very sad. And that kind of dying produces dimethyl sulfide. Now, the important thing is that is a gas, but it's being produced in the ocean. So there will be an increase in the concentration of dimethyl sulfide dissolved in the water, which means that there will then want to be a flux out into the atmosphere because of the Henry's law relationship between the concentration of a dissolved gas and the partial pressure of that gas in the overlying atmosphere. So that's how the dimethyl sulfide gets up into the atmosphere. So that's, I guess, how it's produced, how it gets into the atmosphere, where it comes from. And then we need to think about how it affects the climate. And one one aspect which was missing from quite a lot of answers was that it's not actually the dimethyl sulfide itself that acts on the climate. So it is a climate relevant gas in its own right. It's a greenhouse gas, but when it gets into the atmosphere, there's a lot of oxygen in the atmosphere, and it is rapidly oxidized. Okay, and so this was an aspect that was kind of missing from many answers. An opportunity to whack some nice equations into your answer, get some more bonus points because everyone likes bonus points. So it's rapidly oxidized to sulfate, and it's that sulfate which has a dramatic impact on climate through its action as a cloud condensation nucleus. Now, you could go into some detail about how cloud condensation works. That would be great. But the key thing is that it's acting on the likelihood of clouds forming, and also the longevity of those clouds and the whiteness of those clouds. So we're making more clouds, we're making them last longer and be whiter. Okay, which means that we're affecting the climate through albedo. Okay, and you could add into your answer the equation for the surface temperature and how albedo affects the surface temperature. That would be a nice addition. Okay, because you're really demonstrating the full, I guess, series of logic from producing this gas, from it being oxidized, acting to produce more clouds, and how that affects the albedo, which then affects the climate. Okay, demonstrating that you've got good knowledge all the way through those chain of events. Okay, so that's what we were kind of looking for the first part. Obviously, examples here, very similar to the effects of volcanoes. If you have more volcanoes, more sulfate. But this is a process which happens kind of biologically from the ocean. Okay. Now, so the second part of this question was really, how is this process, okay, of effectively an activity that happens in the ocean and then above the ocean in cloud condensation, how is that going to change in the future? And the important thing is here to think about, how do all of those steps in that kind of chain of logic, how are those dependent on the changing conditions into the future? Okay, and we covered this a little bit in the lectures, this kind of claw hypothesis named after the original proponents, so this Charleston, Lovelock, Andre, and Warren, that photosynthesis, biological production, and ultimately the decay of that organic matter and the production of dimethyl sulfide, this is a series of chemical reactions. If you make the planet warmer, those reactions will go faster, and there'll be more of an opportunity for that material to get into the atmosphere. So one hypothesis is that the temperature dependency of those chemical reactions will mean that more of the dimethyl sulfide will get into the atmosphere, and will have more of a cooling effect. Okay, and therefore is a negative feedback. Okay, now whether that will happen or not depends on our assumptions about what are the environmental controls on all of these processes. Okay, so you need to think about what other things might happen to the ocean, or what other things might happen to the chemistry of these kind of these reactions if the planet gets warmer. Okay, so the reactions might get faster. Okay, one impact of that might be an increased dimethyl sulfide production, but it also might mean a faster rate of oxidation, which means some of it might get oxidized before it can even get out into the atmosphere, which might reduce the flux. One of the real big changes, which is important in looking at how the future oceans will be different, is this idea of stratification. So just quickly, we've kind of already covered that the Earth's ocean has really got two really basic, if we think of it very simply, it has two layers, a surface layer and a deep layer. And if we make the surface layer more buoyant, we make it warmer, okay, so it's less dense. It's harder to mix from the deep ocean to the surface ocean, which means that our flux of nutrients to the surface might be lowered. Okay, which might limit the amount of biological productivity. In this case, this would mean that warmer temperatures might mean less production of biological material, therefore less dimethylsulphide, therefore less of a cooling effect. So in this case, it would be a positive feedback. So more warming, less cooling, therefore more warming, if that makes some sense. So for this question, we're really looking for a description of how the processes might change, and then how those processes will ultimately change the nature of the feedbacks. So there is a risk when answering this question to be quite repetitive with your answers. So you weren't getting credit for writing the same thing over and over again. A few people did that. But what we're really looking for is identifying the different kind of things that could be changing in the future, and how each of those in turn will be affecting different steps in that kind of chain of events when dimethyl sulfide gets produced, and then ultimately its effect on the climate. Okay, so yeah, that's the end of this. Nice picture of some forest for you. Hopefully, this gives you some idea about what we were looking for in the exam questions. If you are watching these videos next year, in the future, I guess all of you will be watching them in the future, but a long time, well, a year in the future. Next year, 2018, I guess. Although you'll all be watching. Anyway, if you're next year students, hopefully this will give you an idea about what the kind of things we're looking for, will inspire you to do a little bit more revision, hopefully. And if you are this year's students, hopefully this will help you with some of the resits that you'll be doing, or not, or will help you in future exams to do that a little bit better, because we all like doing better. No one likes doing worse. Okay.